Okay. 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 Um, all right. We are going to deal with physics today, of course. Um, I'm actually going to ask you to bear with. Okay, I apologize. We're here. This is good. We have a lot to do. I'm going to ask you to bear with me. I probably shouldn't have even stopped the recording. Hold on. I'm going to ask you to bear with me for like 2 more minutes to get something else ready. Um, we had to get back to physics, obviously, but the first thing I want to address, we need to have a midterm exam. We need to have one before too much more time passes. What I just did right now was post an announcement about the midterm exam into Google Classroom, like right this minute. And I don't want to spend this whole period talking about it. We will talk more about it as we get closer, but just in terms of logistics, the what I just posted is essentially well, it's a proposal to make sure it doesn't conflict in a big way with Orgo or one of your other classes or something like that. So let's okay. So the brief overview of how exams work. Well, the brief overview of what I just posted, but it's sort of subject. But it's subject to our confirmation right now. Um, Obviously, exams are never fun for anybody, you or me, and ideally we'd have infinite time to do one and all that, but we don't. Um, so the um, so what I just proposed in a Google Classroom posting is that the midterm exam in physics will be posted a week from tomorrow, which is Halloween, and I apologize for that. But it would be posted a week from tomorrow, no later than 8 midnight. Oh, someone's here. And then it would be due to me right at the beginning of class, at the beginning of this class, Monday, November 4th. Let me back up and explain it. Are we still recording? We are still recording. All right. So the way exams work in this class is we have a midterm exam and we have a final exam. We've one of each. Um, and they are both, well, they are take-home exams. And they are open universe exams. I mean, I will again discuss this in more detail, like as we get over the next few days. They are also, or let's say the midterm exam is also um, deliberately extremely similar to, but not identical to, a practice exam, i.e., which you already have access to in Google Classroom. the the exam that's in Google Classroom already, which was the midterm exam from last semester or the semester before or something like that, that is your practice exam. And you don't turn it in, you don't get a grade on it. It is for you to work and practice. It is to give you as accurate an idea of as possible as to what to expect and how to expect it, like what the format is, what the content is, all that for your actual exam. So the good news behind all of this is um, when you take your exam, it should, whatever challenge it should pose, it should not be some sort of surprise or out of left field thing. The hard part should just be the physics, not guessing what's on it or something like that. Um, so what? So you the we will spend the next couple of classes, or I will be available in the next couple of classes to answer any specific questions you might have about the practice exam that's already available in Google Classroom, but I'll redirect your attention to. And of course, there's tons of videos online where I walk through various aspects of old exams and show you how to do solutions to them. And I will do some of that here in class. But the at the end of the day, or the upshot is that subject to our group confirmation, a week from tomorrow, October 31st, your actual exam would be posted in Google Classroom in the evening, no later than 8 p.m. And you have the full week, then you have Friday, Saturday, and Sunday to work on it. And then you turn it in no later than class time on Monday, the 4th. And again, even though this is going to strike some of you as surprising if you haven't already heard, or it'll strike, like, you can use any resources you want to do this exam. I mean, certainly including past videos from this class, certainly including going on the web in general, including working with one another, believe it or not. Now, there's a flip side to all of this, of course. Like, I'm not as dumb as I look or as I sound. Maybe I am, but don't think it's a joke, and people don't automatically all get A's on it or anything like that. We'll talk about all that. But the fact is, excuse me, the fact is, when I say, or when people have been asking lately, very reasonably, like, when is our exam? The exam is not a one moment experience. It gets posted, you take it home, you do it, you submit it. It's more like a paper or a project or a presentation or whatever. And I'll just say one last quick thing about that, and then I'm going to shut up. I mean, I'll say a lot more about this over the next few days. But as you can imagine, since you're allowed to work, you're allowed to help one another, you're allowed to get help from the web, etc. Since all of that is the case, you can imagine that the issue of the exam, what you get graded on, or what I'm looking for, is not whether you have the correct answers to the questions or not. It's understood that if you're in this class and you're paying any attention, you, in one way or another, will have access to tons of answers to this exam. In fact, some things I'll even go over explicitly, and there's past videos and stuff. So it's not an issue of tracking down the correct answers. It's an issue of, or what the exam is about, is you showing fully on your own, each of you as an individual, that you fully can demonstrate the derivations, the full solutions, the thought process, the understanding that gets you from a question to an answer. In other words, what the exams are graded on is the 5-step method and all of that. What you're showing is as much work. It's a presentation. You're showing, each one of you, even after you help each other or do whatever you do to learn the physics, then you're going home and creating your own document. Ideally, after a draft or two, you're creating a final document that is super neat, super clear, super easy to follow, super self-contained, where in your document, you turn into me here, like on all blank pages, just like you've been practicing with the homework, on all blank pages. Here is a question. Here's the setup. Here's all my work in different colors with annotations, with whatever, here's my version of how to do all of this work. Here's my final answer circled. Here are all my steps. And by the end of the day, what you're showing me, each of you, is a rich, robust document, a personal, authentic, rich, robust document in which you show me that you know how to do the physics for each problem. Okay, so that's what you're graded on. Like, it's not about right answers. It's about, does this person authentically understand the material? And believe me, I can tell, but that's a whole other discussion, which we might have. So, okay, I'm going to look at the chat. I'm sure there's things in the chat. I don't mean to, and sorry, I'm a little bit off kilter today, as you can, like, physically, but I don't mean to be making this sound stressful. I'm not trying to make it sound stressful. In some ways, it's a very manageable undertaking if you approach it the correct way. And what I'm saying is, many of the things that you would normally consider cheating are allowed on my format of exams. But it's not because I don't get that. It's not because I'm not understanding something. It's because my real view about cheating, and believe me, I take cheating very seriously, and people have gotten in trouble for cheating in my classes. Like, it's not something I take lightly at all. However, my definition of cheating is twofold. One is when one person takes an advantage that other people don't have, particularly when one person takes it upon themselves to have an advantage that other people don't have because they were trying to be ethical or, follow an agreement or follow a community. And that one person decided that they were above the community or above the law or is not subject to ethics or whatever. And so in other words, when no one's allowed to go on the web and one person just decides that they're going to go on the web anyway, oh, that's definitely cheating, right? Because they're getting away with saying that everybody else is not getting that advantage just because they're trying to be a good citizen and that person isn't, whatever. So number one, I think what cheating is an unfair advantage. So part of why I do exams the way I do them is I'm saying you all can do everything. So you're all on an even playing field and you all still have time to learn the physics, even if you've been struggling to this point or whatever. You're all on an even playing field. You can all help each other. And again, please also remember, I'm getting off on. Also remember, we're not in a competition in this class. I don't grade on a curve. I mean, in other words, there's no limit to how many A's I'm allowed to give. If everybody literally gets an A, then everybody literally gets an A, and that's awesome. So there's no reason anybody should be trying to edge someone else out with their own secret. Okay, you get what I'm saying. So first of all, you're all allowed to do anything and everything so that you're all allowed to do anything and everything. That's number one. That's why I do it that way. But then number two, what I really do consider cheating and where people have gotten surprised and in trouble. What's cheating is at the end of the day, when you sit down to make your own document and you put your name on your document, I don't care how many people helped you. I don't care if you learn things from Khan Academy. I mean, physics is physics. Like it's not a matter of like citations and stuff like that. However, when you go down to write your own document, then you cannot write down things that you don't understand. Your job in your document is to show through writing that you understand. If you write an equation down that you're just writing down because you got it from the web or whatever, even if it's true, if you're just writing it down to write it down and you don't get why it makes sense or you don't get how to use it or whatever, that's intellectually cheating. And believe it or not, that is utterly apparent to me when people do that. I mean, think of physics like a foreign language that I happen to be somewhat at this point, somewhat conversant in. If we were in a Spanish class, or if we were in an Arabic class, and I asked you to write an essay as a test for like what you did for your summer vacation, you could go all over the web and you could copy down all of these Arabic symbols, and you could like find all of this stuff, and you could put together an essay. You could, where you like copy all the symbols and all the words of like what you did for your summer vacation in Arabic. But you and I both know if you literally don't know Arabic, I'm not saying I do, but if you don't know the language and you don't know the words or the written symbols, and you just try to piece it together from stuff that you get on the web, it's going to be obvious to anybody who actually thinks and speaks in Arabic that you are just clunking around and faking it, right? Well, it's the same thing with physics. The goal of this exam is for you to show that you have gotten more conversant and fluent in the language of physics. So, okay, I've said way too much already. So what I'm going to do is check in the chat. And I'm not trying to freak anybody out. I'm just saying, yes, it's an open universe exam. Yes, you have like 5 days to do it or whatever. What I'm concerned, and yes, we'll say a lot more about it. And yes, it'll be very much based on the practice exam that's already in Google Classroom. And I will make adjustments to as we go. Like if I start seeing if we're close enough to the exam and like we haven't covered something and I can't put it on, then I'll take it out of the practice exam and let you know, whatever. But nothing, in other words, nothing will appear on the exam that doesn't appear on the practice exam. The practice exam is the longest possible version of whatever you would see on your exam. Okay, I'm going to look at the chat. I'm sorry I'm talking so much. But the main concern right now is and you can look in Google Classroom, the posting that I just did, like the official, like here are the dates of the exam. The job right now is for you to tell me, nothing's going to be perfect and nothing's going to work for everybody. But I want to know right now if what I just did was just like literally conflict with Orgo or literally conflict with something that like, you know, messes everybody up in the class. So, okay, so we're worried. So the dates, we're looking to see right now if the dates are vaguely workable for you since I've taken this. Okay, so I'm looking at the chat. Oh, wait, there's nothing in the chat. Wait, so wait, I guess if there's not, okay. So, oh, and it's a small class. Wait, a lot of people. Oh, okay, Annie. Thank God someone said yes. Please shut the man up in the front. Yes, Annie. Sorry.
Yeah, so hi, Professor.
Hi.
Um, on the 29th of October, um, I think Gabriel and I have like we're in the organic chemistry and we have an exam on Tuesday. And then you said you'll post the physics midterm on Halloween, so that would be on the 30th.
31st.
Oh, okay. So there's like 2 days apart. So I think that's fine, right?
Oh, okay. Oh, no, thank you for raising this. Okay. Yeah, it's 2 days. And I do apologize about the Halloween part, but yeah, it's 2 days apart. And also, I don't know if you came in the middle, but I'll post it on in the night of the 31st. But the point is that you have, but then that when I post it, that means you have Friday, Saturday, Sunday to work on it. Like it's due. So your actual moment of it being due is Monday, November 4th. Does that so
Oh, I see. So we have time.
yeah, it's a take home. Yeah.
All
So
right.
is that okay? So does that if that's the case, is that and again, yeah, so I'm gonna pause for a second. Can I just, and I know it's not, and nothing's awesome. No one loves exams, but I- can I just get, uh, well, first of all, can I just get a show of electronic hands that anything what I was just saying sort of makes sense? Do you follow what I'm saying about the exam, you guys? Like just in general? That's one, two. Okay, cool. Thank you, Melanie. Thank you, Annie. Thank you, Vicky. Thank you, Jean. Thank you, Vanita. Thank you, Vicky. Did I say Vicky? Okay. Okay. Then, well, okay. Thank you. So then, and do you guys see oh, that's cool, Hudson. Wow. Oh, and Gabriel. Oh, that's cool. Okay. Do you see, and you guys see the posting in Google Classroom now? Oh, is that, uh, can I get confirmation that because I know there's a lot of information I just like yammered at you, but you see the basic, this description of yes, Melanie. Okay. Thank you. Okay. So that's what it is. I mean, and look, so we're going to move on back to the material now in a second. But if so, I'm going to assume that that date is okay. I'm going to gather from what Andy just said that it doesn't. Of course, you always have tons of work. You know, everybody always has tons of work. But if that's not wildly conflicting with anything that overwhelming, we're gonna. That's what it is. Then we're gonna leave that. Well, all right. Can I? Okay, I'll do this. Can I just get a show of hands, electronic hands? Do you are you acknowledging that even if this is not perfect, do you acknowledge that the dates of the exam are posting October 31st, due November 4th? Can you just like raise your hand to acknowledge that's one, two. Okay. Cool. All right. Awesome. Awesome. Thank you. Thank you. Awesome. Okay. Um, okay. Great. Thank you for your okay. So we're gonna shift gears now. Oh, wait. Oh, I'm looking in the chat. Yeah. All right. So someone just put um in the direct chat. So I won't mention the name, but someone just put in the base in the direct chat. And thank you for doing this. You definitely get points for showing like we're on the same page. Someone just wrote, so basically this is more like a paper where we explain what we did than just like a test. Yes, that's correct. Like, I mean, maybe I would even say presentation. I mean, but like not poster presentation, but yes, it's a big paper in a way. I mean, sometimes when people hand in these exams, they're very, very long, to be honest. So I'm not trying to, but yes, like all what you've ever done on the homework to practice the 5-step methods and stuff, and all my little rules about how you hand in your own pieces of paper, like you don't include my questions and you show what the question is, and then you do all this work. All that stuff that you've been doing on the homework is to practice for this experience. So, yes, what I'm ultimately expecting from each person, you're going to hand in a PDF or a Google Docs or whatever of like a ton of blank, of originally of a clean paper where you're treating the paper like a blue book and you're writing out all of your work to all of the questions of the exam. And yes, and the main way that I grade is first I'm looking like for 5-step method. Like I'm going through looking for all the steps and trying to follow it and see that you really know what you're doing. I mean, so the quick answer what Vincent is saying is yes, but it is important to understand this. Yes. Um, and honestly, this is where too, like you can all help each other and stuff and get each other to understand the basic physics. But those once you feel like you understand something at all, well, it goes both ways. Once there's a question or a topic that you feel like you understand at all, that's where you go to town in this document. Like you should use lots of different colors or draw things your way. Like it will be evident once you take the document seriously, especially if you do a first draft and then and then copy it over, make a final draft, it'll be evident. Those of you who are really starting to see the physics click, you'll actually then feel compelled to kind of get really personal, not personal, but like you'll really show your own style and way of understanding or your way of taking notes or whatever. And you'll find yourself wanting to like really show me that you really get it if you get it. And those of you who don't, who are struggling with the basic concepts or whatever, it's also an opportunity for you to really spell out in detail your thought process. Like it's to advantage. So in other words, the more you understand, the more you want to show your thought process. But the more you don't understand, the more you definitely want to show your thought process because it gives me much more to work with you and give you many more points. It's about process and presentation, right? I mean, all right, I'm dwelling again, but the person in the direct chat is like actually is asking the exact right question. You want to approach this like a presentation of thoughts, not just like a quiz, a big quiz or something like that. It's right. It is possible to get a lot of wrong answers and do really well on this exam. And conversely, it's possible to get a lot of right answers and not do well on the exam. Like, so yeah. Okay. Is there other, there was, and literally, last thing on that, I'm telling you, when you sit down, when I say first draft copy or final copy, like understand when you're doing this exam, when you're writing it out for me, you literally can have things open, while you're doing it. So you could be looking at answers from other things while you're doing it. It's not a memorizing kind of thing, but you just all have to remember that I know that, right? Like it's a huge advantage in a way. It makes the exam much less stressful in a way, but doesn't make it a gift. It's not a silver platter thing because you have to remember that I know that you could be doing that while you're doing the exam. So you have to put yourself in my mindset. Like, what would I be looking for if I already know you could be looking at the answers? What? Okay, you get my point. So yes, direct chat person, totally right. Okay, hold on. I'm going to take a breath. We're going to now talk about physics for the remaining time. Pardon me for one second. I'm going to step away from the computer for one more time just because I'm having a little physical. I'll be right back. Hold on. I'm pausing. Okay. So now and you can still ask questions during the class, obviously, but I'm going to shift gears now. We did the big old duck yesterday, Monday. That's supposed to be a transition. That's a big problem, as I've discussed. That's supposed to be a transition to two-dimensional motion. Oh, but at the end, I was going to say, but if there's any questions about the big old duck, let's address them now. But now, and there probably are. I just realized people pointed out to me right at the end of class. At the end of the, as far as the big old duck, I had made a computation error when I went over it. Sorry, it's been that kind of week, but I corrected the computation error in the PDF. In other words, the PDF that you that was uploaded that you received of the notes from this Monday going over the big old duck, it is correct. It may not be what I was saying when I was rushing at the end of class, but the PDF is correct. And also somebody pointed out that even in one of the videos that I posted where I walk through the big old duck, even there, apparently I made a computation error and I apologize. So if you're looking so the method is correct every time. But if you're looking for the actual numbers to test yourself or to practice, look at the PDF that was posted from Monday. That said, are there any other questions at all about the big old duck problem? Like before I move on, does anyone want to ask anything about that problem that we walked through on Monday? No. Okay. Okay. Then Okay. What we're going to do today is we're gonna try to nail down the concept that is underlying. Well, what we're going to do today is talk explicitly about two-dimensional kinematics, motion in a plane rather than motion in a line. In other words, now we're getting into lab number 3, lab number 4. Well, everything we're talking about today, I'm going to sort of summarize or give you the main underlying point of this is lab number 3, lab number 4, and homework number 7 is what I'm talking. Like, I'm not going to walk through every detail of every one of them right now, but there's something underlying all of those recent assignments. And the thing that's underlying them is that now motion is happening not just in a line, but in a plane. And there's an underlying mathematical method for how to navigate the physics in a plane rather than a line. The concept that's going on is Galileo's principle of relativity, form number 5, which we wrote down yesterday on the board, and you can keep looking back and checking. The concept that's going on here in two-dimensional motion is that every two-dimensional problem is in fact, or every two-dimensional experiment is in fact actually two one-dimensional problems that are occurring simultaneously but independently, right? Now that's a concept that we were first seeing in the big old duck last Monday, that even though something looks like this, it's really this happening while at the same time this is happening, and the two happenings are not affecting each other. Like, that's the concept, right? But now that starts translating into some intricate mathematics. The mathematics that starts translating into is uh, uh, first and foremost a process known as adding or addition of vectors, two-dimensional vectors. So I want to and really this, you first saw this in lab 3, whether you weren't calling it that, you didn't know that it was called vector. I mean, you might have known, but you weren't expected to know that lab 3, the graph paper Desert Island lab, what you were really playing with there were vectors, and what you were really doing, whether you were thinking of it that way or not, was you were adding vectors. And the reason that you were doing that before you did any other labs or anything else is once you know how to add two-dimensional vectors that refer to displacement, then the mathematics are the same for adding two vectors that could mean any other kind of vector quantity, such as velocity or such as force or such as electric field or whatever. In other words, there's a process for adding two-dimensional vectors that comes out of lab 3 that I want to delineate now. And in order to do that, let me back up and be clear about what I mean by vectors themselves. Remember, a vector quantity is a quantity with magnitude and direction. That's what a vector quantity is, right? Like, remember, like distance is not a vector quantity, it's a scalar quantity. Displacement is a vector quantity. Average speed, not a vector quantity, but average velocity is a vector quantity. Why? Because it doesn't just take into account magnitude, it also takes into account direction. Hold on, that's what a vector quantity is. But now, at this point in the year, or once we're in two-dimensional land, we start using something called vectors to represent vector quantity, to represent vector quantities. So from that, so what this says is a vector is an arrow used to represent a vector quantity. The length of the arrow represents magnitude. The tip to tail orientation represents direction. So from now on, we're going to be drawing these arrows on the page. And every time we draw an arrow, well, just what it says, it it represents a certain vector quantity. The arrow could represent a displacement. It could represent a velocity. It could represent an acceleration. It's a force. But the reason we use the arrows is that an arrow has two properties. It has a size, a length, and it also, like, if it's literally an arrow, like it has a tip and it has a tail, then the arrow points somewhere on the page. So the way it is oriented, its tip and its tail, we use to represent the direction of the vector quantity. Note, okay, now that we're in two dimensions, um, direction becomes, whoa, sorry, direction becomes, oh my God. What? Sorry, those pop-ups. Okay. Now that we're in two dimensions, direction is a slightly more intricate idea. Like when we were in one dimension, direction just meant forward or backward, or north or south, or east or west. In other words, plus or minus, right? You could capture the entire degree of freedom on one axis uh, by distinguishing a plus from a minus sign. Now we're in two dimensions. So direction, as you saw in lab 3, direction is subtler. The way we talk about um, directions now is with, I mean, there's various choices, and in a math class, you might do it slightly differently from the way you do it in a physics class. But in a physics class, we're actually interested in space and time. So what we tend to do with direction in two dimensions in physics. Okay, in physics, as always, we would have a coordinate system labeled in advance, defined in advance. We would make a decision. Like we would say, okay, there's two axes now, there's two dimensions. So independently on each axis, we would make a decision. Like we would say, this is north, this is south. North is designated positive, south is designated negative. And on the other axis, this is east, that's designated positive. This is west, that's designated negative. In other words, on each axis, we still make a decision about what's positive and what's negative. And on each axis, we relate it to general points of the compass, to general space. And with that in mind, we could draw this. This would be an example. Okay. This yellow arrow is an example of a displacement vector. It represents a displacement quantity, right? This arrow represents a displacement, let's say, of 15 meters. So it's meters, right? Because it's displacement. So the magnitude of this arrow, let's say, is 15 meters. Um, and its direction, let's say, is 30 degrees northeast. Like, notice how we say that. We don't say positive 30 degrees or negative 30 degrees. Or we don't say something like 120 degrees. I mean, even, and so if it were pointed the other way, if it were pointed like this, we wouldn't say 120 degrees or something like that. We would say 30 degrees northwest, or so, like in other words, I'm saying we always give an acute angle, a positive acute angle, and then 2 points of the compass. When we say that this thing is 30 degrees northeast, what we're really saying is, what that really means is, like, what northeast really means is north of east. We're imagining, we're comparing it to imaginary reference line that just points directly east. And when we say 30 degrees northeast, what we're saying is we have opened up a vector 30 degrees north of the eastern line. Okay, I'm over talking this again. So that would be an example of a vector, of a displacement vector. You could just as easily have, you could have a vector, and the idea is that if I wanted to make a vector that was 10 meters at 30 degrees, I would draw an arrow that's 2/3 as long as that one. Like, the idea is that you're drawing these arrows to some scale. Okay, let me cut. And the other idea is that could have been an arrow that said 15 meters per second at 30 degrees northeast. Then it would be an arrow that's representing a velocity vector rather than a displacement vector. Like, the arrow can be used, and so a 15 meter per second velocity vector would be that much longer than a 5 meter per second velocity vector, and it would represent someone going that much faster at that moment, at that point in space and time. Okay, so this is what a vector is in general. But now, I want to the meat that I want to get to is, and what has been happening, like in lab 3 and in homework 7, is oh, okay. Well, I'm going to show you now with with the 30 minutes we have left is what to do when you have two or more vectors that you want to add together, two or more two-dimensional vectors that you want to add together. The first thing I'm saying is I'm going to show you how you add vectors to get, I'm going to show you how you add displacement vectors together, which is, again, in effect, what you were doing in lab 3, whether you thought of it that way or not. I'm going to show you how to add displacement vectors together. I want you to see two things as I'm showing you. One, that whatever I'm doing with displacement vectors would be the same method, whether they were velocity vectors, acceleration vectors, electrostatic field vectors, whatever. I'm showing you how to add vectors together, and I'm using displacement vectors as an example because they're the clearest to picture in our minds at first. Second of all, I want you to see that the method that I'm going to use to add vectors together, the method we'll always use in physics 203 or physics 204 or whatever, the method is known as the component method. The method asks us to resolve vectors into components and add the components together. And I want you to see that this component method, it could possibly look like it's out of nowhere to some of us, but what it really is, this component method is just a way of embracing what I keep saying over and over again, which is that even if something looks like it's a two-dimensional quantity, it's really two one-dimensional quantities occurring simultaneously yet independently. So I'm going to now show you the component method of vector addition, which is really a way of applying Galileo's principle of relativity to two-dimensional displacements. Okay, so here we go. Okay, so here's the example. Say vector 1 is 15 meters of displacement at 30 degrees northeast. So I walk, like to say, I start at some point, like you call point A. I walk 15 meters at 30 degrees northeast. Then I stand there. And then I walk 5 meters at 60 degrees southeast, right? And I want to know. So first I walk northeast, then I walk southeast. And I want to know, sorry, I want to know where I end up as compared to where I started. I want to know specifically how far away I end up and specifically in what direction. Like not just northeast or southwest, but like what angle. right? So I want to know my total displacement, magnitude and direction in 2 dimensions for this situation. I want, right? Okay. Um, so we're still using all our same definitions of physics. Like displacement still means the difference between final position and initial position. We're still including direction and magnitude. It's just now it's a lot. It seems more complicated because now direction includes this whole variation of angles. So I'm going to have to do so. So I want to add these two vectors together, but I want to add the vectors together. I So I'm going to have to do some work. Let me make a couple of things clear right away. Okay. Or the two things I want first of all, this is a math problem. I mean, I cannot do this in my head. If you think that you can see the answer right away in your head, if you think you can see the magnitude and direction of the answer right away in your head, you may be oversimplifying something. Like if we're adding two vectors, but we're adding the vectors. If you just add the numbers 15 meter and 5 meter in your head and say 20, you're doing something, but you're not doing this. 15 plus 5 would be the total distance that the person would walk. Like, yes, if I would walk, if I go like this and then I walk 5, sure, I walked a total of 20 meters of distance, but I will not end up 20 meters away from where I started. And that's what I'm looking for. I'm looking for the magnitude and direction of displacement. How can I tell that? Well, if you want to capture, if you want to represent what's going on here, whenever you add, and this is a truism now, if you ever want to add two vectors together of any kind, it's easiest to see the following with displacements. You place them tip to tail. Like if you want to draw a diagram, like again, this is like what you did in lab 3. If you want to draw a diagram of this situation, you draw the first vector. The first vector is like this. And then and you try to be as to scale as possible. From the tip of the first vector, you draw the tail of the second vector. So the second vector set to go, yeah, southeast. So at a bigger angle. So I would do something like this. Now, I'm not drawing this perfectly to scale, but the better to scale you do, the better. In fact, well, I'll leave it at that. Like, well, no, okay. I'll do this a little bit better. Sorry. Okay. If I put these two vectors tip to tail, the that represents addition. And the answer to the addition problem, the answer to the addition problem the answer to the addition problem can be represented by a vector that goes from the original tail to the final tip. In other words, this yellow arrow is what actually will have happened at the end of the day, right? I will end up somewhere. I mean, and the more perfectly to scale this thing is drawn, the more I can literally use rulers and protractors to find out the final answer. Like that's the thing about vectors is they're not just rough representations. They're representations the way graphs are representations. Like if you draw them accurately, then you can actually use the drawing as a computation tool. But what I'm trying to say right now is if you look at this picture represents the addition of the two vectors and shows you how the total displacement is not going to be, I mean, I hope you can see in the picture, it's not going to be 20 meters. It's going to be shorter than 20 meters. And it's not going to be like 30 degrees plus 90 degrees plus 60 degrees equals 90 degrees or something. Like you can't just add the degrees together and get the final degree. It's going to be some weird angle that's less than 30 degrees northeast. So how do we get it? And I know we only have 17 minutes. How do we analytically? So this graphically depicts the addition tip to tail. You always add vectors by placing them tip to tail visually. But how do we analytically compute the exact answer? This is how we use Galileo's principle and components. We break each vector. Well, I'll write on the next page. The answer to how we actually do this in the 17 minutes we have left. And again, I know it doesn't matter. Whatever I'm doing right now applies to all addition of all vectors, and it can be 3 vectors, 4 vectors, 5 vectors. Like this is the process of we zoom in on each individual vector and break it up, or what we call resolve the vector into its independent components. I.e., we take vector 1. Vector 1 was 15 meters at 30 degrees. What we say to ourselves is, aha. 15 meters at 30 degrees northeast. We say, aha, a vector that's going northeast is really a vector that is going somewhat east, while at the same time it's going somewhat north. Or if I walk 15 meters in a northeasterly direction, that means I have walked some amount in an easterly direction, while I've also walked some amount in a northerly direction. The only question is how much amount of each, right? In other words, I'm saying, if we just said a second ago that when you place 2 vectors tip to tail, that means addition, then I can view this vector itself as the tip to tail addition of 2. So remember, so the tip to tail thing is important. Like, remember, add means tip to tail. That's much more important than it might seem. So I'm literally going to say, aha, 15 meters at 30 degrees northeast. I can resolve it. I could say, oh, that means I walked some amount east plus some amount north. You see the tip to tip, right? And I'm putting arrows on this on purpose. 15 meters at 30 degrees northeast really is some amount east plus, like independently, but at the same time, plus some amount north, right? And as to how much amount, well, how much, so if I could just figure out how far this is and how far this is, I would know something very important. Can I figure them out? Yes, I can use SOHCAHTOA. I'm going to do this. So, right? Like I know, for example, the cosine of 30 will equal the adjacent over the hypotenuse. Well, it's the adjacent side I'm looking for. So the adjacent will definitely equal the hypotenuse times cosine of 30, and et cetera for the opposite. In other words, I'm cutting to the chase. I'm saying this side right here is definitely 15 times the cosine of 30. And this side here is 15 times the sine of 30. Now, those are numbers on my calculator. Right. In fact, I should get my calculator. But before I even plug in the numbers or whatever, I'm going to do the same thing to the other vector. The other vector looked like this. It was 5 meters at 60 degrees, right? So I'm saying same thing. That vector really was the equivalent to going 5 cosine 60, while at the same time, but independently going 5 sine 60. I mean, 5 cosine 60 to the east while going 5 sine 60 to the south. Now, why? Now, these are numbers, right? These are actual amounts, right? Like 5 cosine 60 is 2.5. Like you do it on a calculator. And 5 sine 60 is 0.866 times 5. Right, which is 4.33. And same thing over here. 15 sine 30 is 7.5, and 15 cos 30 is approximately 12.9. So what's the significance of all of this? What this means is, if I look at my original diagram, when I walk 15 and then I walk 5, what I really did, like remember, a two-dimensional physics problem is really two one-dimensional physics problems occurring simultaneously, yet independently. So I could say what's really happening here. I can make an XY chart. I can say that actually what happened, I'm going to divide the world, in other words, into two dimensions, the X dimension and the Y dimension, and say they're not affecting each other. And this is what you were seeing in lab 3. They're not affecting each other. They're each occurring according to the laws of physics. So in the X world, in the east-west world, first I walked 12.9 meters to the east. And remember, we've been saying east is positive. So I walked 12.9 meters to the east, right? While in the north-south world, I walked 7.5 meters to the north. Then I walked 2.5 meters to the east, but I walked 4.33 meters to the south. So that gets a negative sign, right? If we're watching our pluses and minuses. And at the end of the day, I could just add those numbers up like regular numbers. Like again, what I'm trying to emphasize is to add the vectors, you can't add the magnitudes. You can't say that your total displacement was 15 plus 5. That doesn't work because those are in two different directions. But if you break everything up into common directions, like you did in lab 3, you could certainly add up 12.9 and 2.5. We just walked 12.9. I think you see what I'm saying. So I'm going to independently add these up. I'm saying this is like 15.4 in the east direction, and 7.5 minus 4.33 is like 3.17, both positive, right? So at the end of the day, what I've done equivalently is I've walked 15.4 meters to the east, while at the same time, but independently, walking 3.17 to the north. I know it's north because it was a positive number. Sorry. So what did I do at the end of the day? Whenever you place vectors tip to tail, you're adding them. So I went 15.4 to the east plus 3.17 to the north. So equivalently, what I did was I did the Pythagorean sum of these two things. Like at the end of the day, like Pythagorean theorem is what I'm doing, right? So, so the magnitude of the final displacement would be the Pythagorean sum of those two sides, and and the direction would be whatever that angle is between the tails. Now, how can I get the angle? How can I get that angle? Well, I do SOHCAHTOA again. Like I know, and I always use tan. You could use a bunch of things, but I know that the tangent is the opposite over the adjacent. So therefore, the angle itself is the arctan, the inverse tan, doing it backward, tan to the -1 on your calculator. Right. So I'm saying a number of things. I know class is just about over, but first of all, sorry. Oh, okay. Wait. Good question, Andy. Hold on. Let me see if I can get that. Let me address that in 1 minute. Let me first summarize this. First of all, if we did one problem today, and it's a practice problem, like this wasn't literally a problem from any of the homeworks. It's just like trying to capture the concept of a lot of the homework problems. So the one problem we just did was if you have two displacement vectors and you add them together, what's the final displacement? Like that's what we're doing, right? We're saying if we walk like this and then we walk like this, where did we end up relative to where we started? And what I'm claiming is the answer is if you walk 15 meters and then 5 meters, and you 50 meters at 30 degrees northeast, and then 5 meters, 60 degrees southeast, I'm saying you will end up 15.7 meters away from where you started. Like in this original picture, this picture here, I'm saying that yellow line, that yellow vector in the picture is apparently about 15.7 meters long, not 20, not 5, not 5, like a little bit bigger than 15, a little bit bigger than each of 15 and 5, but not bigger than the sum of them. Anyway, you're about 15.7 meters away. And the direction you headed in was about 11 degrees northeast. Now, by the way, even this really rough sketch that's done really badly, not so well to scale, captures that, right? It's a long line that's longer than 15, but not much longer than 15. And it's at a shallow angle that's northeast, but less than 30 degrees. So I think what we're doing makes sense. We're saying you would walk in a northeasterly direction, but not as dramatically northeast as you started because your second vector shoved you back a little bit south, right? Notice though that the actual answers that we get at the end of the day, I could not get in my head. 15.7 and 11 degrees northeast, the way we got them. Now I'm going to address Annie's question. The way we got and this is the final answer. The final answer must include a magnitude of displacement and a direction of displacement, because displacement is a vector. It has magnitude and direction. And the direction has to be very specific. It has to be an angle with points of the compass, right? But that's what I have here. 15.7 meters approximately, and approximately 11.6 degrees northeast. Now, what I did was the component method. What Annie's asking, it's a very important question. I don't want to blow it up. It's a very important question, but I want you to hear the answer closely. She's suggesting some other triangle knowledge that she has. Like, we all know, we have a bunch of knowledge about triangles in general from trigonometry. And there's a bunch of laws, such as the law of cosine, which are very powerful laws, which do a lot for us. However, and sometimes in certain problems, they can look like they give you advantages or help you out sometimes. But to be as honest and clear as possible, I did not use the law of cosines here, and I do recommend not using the law of cosines. The method I just used here, where I took each vector and broke it into where I took each vector and made it into its own right triangle, got the legs of that right triangle, then added the legs together, and then made one final big right triangle. Like, that's what I just did here. I broke each vector apart into its own right triangle. I took all the legs of the right triangles and added them individually, independently in like an XY chart. And then I put the results back together in one final right triangle. This is what I'm saying. I recommend that you always, this will work. This method will work for all different types of problems. And no matter how many vectors you have, it will work. And no matter what kind of triangles you have. The thing about the law of cosines is the law of okay, I don't want to get too bogged down now, but law of cosines sometimes will look good depending on the triangle that if you were looking at this original triangle, you might think you could get some knowledge about it with the law of cosines, but it would work there, but it wouldn't necessarily work for other triangles, I guess is the fastest thing I could say. And it doesn't capture the physics of what's going on. The bottom line is we're not just looking at triangles. We're not just looking at sides of shapes like geometry or trigonometry. We're ultimately trying to look at directions through space. So the method that I'm trying to teach everybody that will work every time is being able to stand back and say, even if something looks like it's two-dimensional, it's really always a bunch of two one-dimensional things. So that's a very long answer, but basically, I love the law of cosines. Don't get me wrong, and it's very insightful to bring it up. I don't recommend it actually for these kind of problems. But okay, that's 12:05. Oh, okay, cool. Thank you. You're very polite. Thank you. Okay. So that's it. We'll talk more about this stuff in exams or whatever on next Monday. But you've been very patient. I know it's been a clunky class. Thank you all very much. Have a great weekend.
Thank you, Cliff.
Thank you. Bye.
Nice speaking, Professor.
Are you
Bye.
going to release the exam again on the 31st?
Yeah, I'll release it no later. Hold on, I'm going to stop the recording.